Hey, what's up guys? This is the video where I'm going over the chemistry practice IA number 1, and this IA is going to cover entirely atomic structure. So anything that you might see from Unit 0, anything we learned from Unit 0 won't be present in this particular IA. And so before we even begin, you got to make sure you have your reference tables out with you because a lot of these questions are going to rely on those reference tables. Alright, so let's begin. Number 1. What is the number of electrons in an oxygen atom? So the key word I want you to focus on is that we're looking at an atom, because the difference here is that an atom, we assume it's neutral. Oh, that's ugly. You can't even see it in the black background. All right, screw that. So the atom we think is neutral. But on the other hand, the ion is non-neutral. And when you're neutral in the atom, same number of protons and electrons. So these guys balance each other out. But for the non-neutral atom, the ion, these are not equal to each other. So we're going to see different numbers. And so how do we figure this out? The electrons for a neutral atom for oxygen. You got to look it up on the reference table. What is the number of protons for oxygen? And you'll see the atomic number is the same as the number of protons. And you'll find that oxygen has an atomic number of 8. Therefore, it has 8 electrons as well. All right, number 2. What is the total charge of the nucleus of a potassium ion? Oh, no, sorry, potassium atom. Okay, another keyword, nucleus. So what goes on inside the nucleus? Let's think about that. So the nucleus has both protons and neutrons. What are the charges of these particles? Protons are positive, neutrons are 0. So if we get our charge from the nucleus just from protons, we need to figure out how many are there for potassium. And potassium, again, you gotta look up on the reference table. Potassium has an atomic number of 19. So that means there are 19 of these guys. Potassium has 19 atomic number, 19 protons. So this comes out to a positive 19 inside the nucleus. And if we're talking about the atom, we have to take into account electrons too. But we're just talking about nucleus. Number 3, which particle has the least mass? So we're looking for the smallest one in size. Protons and neutrons are equal in size. So their masses are the same. A helium atom, on the other hand, is big. So a helium atom has already more than 1 proton. This happens to have 2 protons. So that itself is big, including the neutrons too. The electron, on the other hand, is negligible mass. So we barely count it anyway. Negligible, we ignore it because it's so little. So when talking about mass, we think electron is the smallest particle inside the atom because it's so small, so negligible, we ignore it. Okay, number 4. The nuclides uranium-238 and uranium-240 are classified as, so I want you to look at these choices. We have not talked about isomers, but we have talked about isotopes. And isotopes, hint hint is going to be our answer. Never mind, I thought that would work. Guess not. Alright, sorry, I had trouble deciding on a color. Isotopes, same element, different mass. Different mass number, and you could see 238 and 240 are the different mass numbers. So uranium-238 and uranium-240 each have different mass numbers, but they're still both uraniums. So that's choice 3. Isotopes of the same element. Okay. Alright, number 5. Here we have a table of the 3 subatomic particles, protons, electrons, and neutrons, shown for 4 different atoms, A, D, X, and Z. Which 2 atoms are isotopes of the same element? So focusing on the word isotopes, we mean same element. So that means when they're the same element, it has to be same number of protons. Equals same protons. But isotopes mean different mass numbers. And when we think of that, we have to think of different protons. Sorry, not protons, neutrons. So we want the same number of protons. We look at A and D for sure. Same number of protons, and just to double check, they also have the same different numbers of neutrons. So isotopes, the same element, same number of protons, but different mass numbers, different number of neutrons. That's A and D. Number 6. Which change occurs when an atom in an excited state returns to the ground state? So going from ground to excited, that's from low to high. An electron has to absorb energy to go up to higher state, to become excited. But when you go from excited back down to ground, you have to release that energy. So this energy is released. Nothing is changing about the number of electrons, they're just changing positions, basically. So energy is emitted, the same as saying released. Number 7. The gold foil experiment, think Rutherford, led to the conclusion that each atom in the foil has a dense positive center because some alpha particles directed at the foil. So, alright. So he came up with 2 main conclusions from his experiment. The first one was empty space, mostly empty space. And the second one is dense center, basically the nucleus. We have to think about the reasons why he came up with that. From mostly empty space, it's because the alpha particles went through for this one. So if the alpha particles went through the foil, that means it had to go through some space. That hence why mostly space is one of the conclusions he came up with. For the other one, dense center, if you hit against something, you're going to bounce off it or stick to it. So the main evidence that showed him that this atom has a dense center is because the alpha particles were deflected by that nuclei in the atom. Okay, so that is choice 3. Number 8. Which particle has a mass of approximately 1 atomic mass unit? So we're looking at each of our choices. We didn't learn about a beta particle yet. We didn't even learn about an alpha particle either. But we did learn about electrons and neutrons. So electrons have negligible mass. We ignore its mass. Too small. But the neutron we did talk about with the proton. And as the question asks, it does have a mass of 1 AMU, 1 atomic mass unit. And that's the same for a proton also. Okay, number 9. Which quantity can vary among atoms of the same element? So when we're talking about the same element, we need to make sure protons stay untouched. Protons stay same. They stay the same. Well, that's not even the right spelling. Stay the same. So that also affects the atomic number. Number of electrons versus mass number. Both are true, but key word is atoms. We're not talking about ions. And when we say atoms, we assume neutrality. So this number of neutrons is also going to be the same. Mass number can change between atoms of the same element. That means different number of neutrons, which can change. So you got to think isotopes with this. Number 10. Which atom in the ground state has an outermost electron with the most energy? So for number 10, we have to think most energy. Those are the ones at the higher energy levels. So nothing down in the first level. And when we say outermost, we're thinking valence electrons. So which one has the most energy levels, so to speak? Because the one with the most energy levels has the most energy. And you're going to look in your reference table and look at each of these guys. So I'm going to pull it up in a bit. Alright, here we are with the periodic table. And so we're looking for the one with the most energy levels. And so we're looking at each of these: cesium, potassium, lithium, and sodium. And they're all located in this aisle. They all have the same number of valence electrons, 1, 1, 1, 1, 1. But we're looking for the one with the most energy levels, and you'll find it with the one with the most numbers, and that is cesium. It has 6 energy levels listed there, because there are 6 numbers. And so the one with the most energy is cesium, CS. Alright, number 11. All calcium atoms have the same what? So let's look at calcium. Its atomic number is 20. So that means it has 20 protons. It'll always have the same number of protons because that's how you identify the element. Look at these guys. They all have different atomic numbers, and so they're going to be different elements. As long as it's still 20, it's still calcium. And that is our answer, the atomic number. Because atomic number defines the element. If it's not the same number, it's a different element. Alright, number 12. Let's do blue this time. Which statement describes how an atom in the ground state becomes excited? So to become excited, to go up higher, you need energy. So it needs to absorb energy. Cross off 3 and 4. So you absorb. And you have to go up to a higher level. Choice 1. Choice 2 is wrong because it talks about lower level. Alright, number 13. What is the total number of valence electrons? So we're looking at the last number. In the atom of germanium in the ground state. So germanium on the reference table is GE. Ground state configuration is given at the bottom. So 2, 8, 18, 4. You should be looking along on your reference table or on the screen. Let me pull this up bigger. Zoom in. Ooh, here you go. A little disorienting. 2, 8, 18, 4. Valence meaning the last level. So there are 4 of them, because that number means 4 electrons in the last level. Choice 4. Alright. Let's do purple. Number 14. Which atom in the ground state has the same electron configuration as antimony ion Sb3- in the ground state? Okay, this is a little tricky. So we need to find antimony. That's Sb. So the original configuration in the ground state for antimony is 2, 8, 18, 18, 5. However, it's talking about the ion Sb3-. For 3-, you have a negative charge. So this means negative ion, more electrons. So that means we gain 3 electrons. And where do we put those 3 electrons? We put them in the end. Okay? So we add those 3 electrons and put them to the last level. So this new configuration, I'm going to write out here, is going to be 2, 8, 18, 18, 8. Okay? So that's how we do that. When you gain 3 electrons, you put it into the last level. If you take away 3 electrons, you lose them. You just take them away. And so we're looking for an element with the same configuration as this guy over here. 2, 8, 18, 18, 8. And that is over here. Xenon, Xe. Over there. Oops, right at the bottom, scraping by. Alright, 15 to 20 on this side. The atomic mass of titanium is 47.88 atomic mass units. This atomic mass represents, so by definition, we have to think about what it means. And if you look back in your notes, average atomic mass is essentially a weighted average. weighted average of the most abundant isotope of titanium, or weighted average match of all the naturally occurring isotopes of titanium. So if we remember from our examples, we could already cross off choice 1 and choice 2. Because they talk about total mass, but we're not concerned with that. But in actuality, we're talking about weighted average mass, so it's between 3 and 4. Do we take into account just one isotope, or do we take into account all the possible isotopes? And if you recall our problems, that's choice 4. We take into account all of the possible occurring isotopes for a specific element. And then we take their percentages times their mass numbers, and we combine it all together. And that's how we get that weighted average mass. You're not just taking it for one piece, you're taking it for multiple pieces. All right, number 16. A specific amount of energy is emitted when excited electrons in an atom and a sample of an element return to the ground state. That's a lot of words. This emitted energy can be used to determine the what. Okay, so think back to that bright line spectrum. It releases energy in the form of colored light. And what is that emitted energy? What does it tell us? What is even the purpose of this bright line spectrum? It's to identify the element. That's how we identify them, because certain elements, remember, release certain colors. Number 17. Compared to the energy and charge of the electrons in the second shell of a beryllium atom, the electrons in the first shell of this atom have what? So we're focusing on first shell and comparing it to second shell. So first shell versus second shell. First is lower, second is higher. Because it's in a lower level, first energy level has less energy. And then second level has more energy because it's higher. Okay, so we could cross off, focusing on the first level, we could cross off 3 and 4. Now how about the charge? All right. Now let's just talk about electrons. Do electrons have different charges? No. They're all the same type of particle, same type of charge. So all electrons are -1 in charge. So nothing is changing in terms of charge. All it is the energy. All right, number 18. Remember I told you the most important definition you kind of need to remember, take to heart, or maybe tattoo it on your forehead? An orbital is defined as a region of the most probable location of what? The electron. So when talking about orbitals, you need to think about electrons. It's the most probable location of these guys. So by word association, think of that answer. Okay. 19. An atom that contains 4 protons, 6 neutrons, and 3 electrons has a mass of what? So an atom that contains 4 protons, let me break that down, there's too many words. I can't English, guys. Now talking about mass, which particle do we neglect? We neglect this guy. Too small. But these protons and neutrons each have mass. So there's 4 of them, and they each have 1 AMU of mass. Not grams, AMU, atomic mass units. Because their actual size in grams is really, really, really small. It's decimals, basically. So this one's going to have 4 AMU, and this one's going to be 6 AMU. So altogether, that's going to be 10 AMU. 10 units. Choice 3. So mass, only consider protons and neutrons. So think to yourself, tattoo it on your forehead or something, or on your arms. Don't write it on your arms, because that's cheating, but tattoo it on your forehead and everybody else will see it. Mass, we only consider protons and neutrons. Actually, don't tattoo things to your forehead. That's cheating, actually. Number 20. The nucleus of an atom of cobalt-58 contains what? Alright, so what does this number 58 even stand for? That's the mass number. Again, mass number is protons and neutrons. How do we find the protons? Well, we gotta look it up on the reference table. Let's pull it up. And bam, here's our reference table. Cobalt is CO, right here. Oop, sorry. Let me undo that. Cobalt's right here. It has an atomic number of 27, so it has 27 protons. So we're looking at choices 1 or 2. Now, how do we figure out the neutrons? If we have 58 total as our mass number, and we have 27 protons, we need to figure out how many neutrons. I don't want to use X as a variable. Alright, so 58 minus 27 will get us the number of neutrons. And so 58 minus 27 will get us 31 neutrons. And that is choice 1. That is how you figure out the number of neutrons from the mass number. Okay, so number 21. We need to find the 2 notations that represent isotopes of the same element. So for this notation, we need to make sure we have the same element. So first off, we could cross off 2, 3, and 4 because they're all different elements. Well, that's easy. You could easily eliminate and see that's choice 1 because it's the same element, same symbol. But what is the difference here? Let's look at it. Okay. So the bottom number represents the atomic number. That's the number of protons, that's the identity of the element. Whereas the top number gives us the mass number. That's the one that's different between isotopes. Okay, to repeat myself, but you're going to see that it's a repeating theme here. It's a recurring theme. And number 22, let's see. Which element is not present in the mixture? So we're looking at the one that does not match up with the lines on the mixture right here. So we're going to make sure all these lines match up with elements to see that it's present. If there's something that doesn't match up, then it's not there. And we're going to see here that it's element X. Right here, you have 2 lines over at the end of X that don't show up on the mixture. When that happens, it's not there. You could rule out that an element is not present in that mixture. So it's choice X. If you look at each of the other 3 elements, A, D, and Z, you'll see that each of them have all their lines matching up inside the mixture. All right. 23. Which conclusion is based on the gold foil experiment and the resulting model of the atom? So in an earlier question, I wrote the 2 main conclusions, empty space and dense positive center, called the nucleus. So right off the bat, we can see it's choice 1. Choice 2 says the nucleus has no charge, but that's false, it's positive. Choice 3 is the opposite of everything we said. And choice 4, it has the first statement being the opposite. It is mostly empty space, not hardly. All right, number 24. The atomic mass of an element is the weighted average atomic masses of all the naturally occurring isotopes of the element, not any artificial, it's all natural. All right, 25. Which electron configuration represents the electrons of an atom of neon in an excited state? So we need to have out our reference table and find neon in the ground state. So that's given in the reference table. So neon is Ne, and you'll find that its ground state is 2-8. Excited state, we take any electron from a lower level and bring it up to the higher level. So we can't go over 9 on this one because these guys are at their limit. So what we can do is bring 1 electron to the next level, higher up, while also maintaining the same number of electrons. And so the question that best, the answer choice that best fits this is choice 3. And we got to make sure that both of these configurations still add up to the same number of electrons. This one's 10, and this one is also 10. So you can see that the number of electrons stays the same, but they're just rearranged in different order. different locations. Alright, 26. Which numerical setup, so we're not looking to solve it, we're looking to just find the equation set up with the properly substituted values. So which of them can be used to determine the atomic mass of naturally occurring lithium? So the way we're going to do it is that we're going to take each of these atomic masses and multiply them by their natural abundance percentage. However, you need to turn these guys to decimals. So that means 2 places to the left to make it into a decimal. So this one's actually 0.076 and this one is 0.924. So you need to do that before you multiply anything out. And after you get those products, you add them all up. So whatever these numbers is and whatever this number is, you add them all up to get their final answer. So we need to find a setup that best fits that. So we're not dividing by anything, no division here. And looking at choice 1 and 2, choice 1 didn't convert those percentages into decimals, so we can ignore that. Whereas choice 2 does, and that's correct. We take each of those atomic masses, multiply by their percent abundance in decimal form. So that's what you need to do first before anything else. Number 27. Alright, oops, did something iffy there. Alright, 27. Which term is defined as the region in an atom where an electron is most likely to be located? And that's the orbital. Nothing changed there. Same question as before. 28. The most common isotope of chromium has a mass number of 52. Which notation represents a different isotope of chromium? So isotope, same atomic number, different mass number. So this 52 is not going to exist anymore. So we can get rid of that 52. Anything with 52 we get rid of. And we're stuck with 2 and 4. So we got to keep in mind that X represents at the top mass number. So that one has to be different. But the Y down at the bottom is the atomic number. And a chromium's atomic number happens to be 24. So in actuality, it has to be Cr 24 and anything different than 52. So let's say 54. And that's choice 2. Number 29. Compared to the charge of an electron, the charge of a proton has what? So, okay, we know electron is negative, proton is positive. Now look at these words, magnitude. Magnitude means the value of it. The sign means positive or negative, direction. So we know they have opposite signs. That's for sure. So we're looking at the value of the charge. Electrons are -1. Protons are +1. So we can see the value, the number, is the same magnitude. They're both 1 in value, but opposite in sign, negative and positive. Alright, from that explanation, we should get choice 1. Oop, that's wrong. Oops, choice 1. And final question, which electron configuration represents the electrons in an atom of Sb in an excited state? So I have a reference table. You should look up the electron configuration for Sb in the ground state. Alright, so you should find that antimony Sb is, oh, that's an ugly 2. Let me erase that. It's 2, 8, 18, 18, 5. An excited state, meaning we're taking an electron from a lower level and bringing up to a higher level. We could either bring it up here or to another level, and let's see. We could cross off choice 2. I keep doing that. Cross off choice 2. We could cross off choice 4, and I want you to see and focus that we didn't change anything but take 1 electron away. We didn't even move it anywhere. So you need to take away an electron and move it somewhere else, which is not the case for choice 4. But you can see in choice 1 that is the case. It took 1 electron from here and moved it up higher. In choice 3, it just added an electron without really keeping in mind that we need to keep the same total as before. It just added an electron. It didn't really take 1 away and put it elsewhere. So for that, we're going to pick choice 1 because that's the correct answer. And we reached the end of this 30 question practice IA. Yeah, that was really long. I'm really rusty with making videos. But anyway, I hope that was helpful. If you stuck on some questions, feel free to go back or check out the content area videos I'm going to post up later. Alright, best of luck, guys.